Hello everybody, this is Dr. Hussein. Welcome back um, to this semester 1 in 2020-2021. I'm happy to start with you discussing topics and models related to electrical and electric circuit analysis. Before we start, it's worth to highlight the course learning outcomes, which will cover what we are going to come up with from this course. So you can see that we have 5 points, 5 learning outcomes need to be covered. The first one is to describe and analyze steady-state AC circuits, and the second one is to identify and solve balanced three-phase system, and third is to determine and identify the operation principles of semiconductor device, where we will discuss diode, transistor, and so semiconductor. Fourth is to classify and solve bipolar junction transistor and MOSFET, metal oxide semiconductor field effect transistor biasing circuits. And finally is the classify and solve small signal model for the BGTs. Now, these course learning outcomes supposed to linked to program learning outcomes. As you remember, we have 11 program learning outcomes, and the course learning outcome, the 5 I just mentioned, are here related to these to these 11 program learning outcomes. We will use 3 references here: circuit device and system, which is by Smith and published by John Wiley and Sons, and Navi, which is schematic outline electric circuits, and Humbly electronic and topic approach to computer-aided circuitry design. But usually I advise to focus more on Humbly books, electrical circuit technology, electronics. All these books are related to our course. Now, as you know, this semester we will follow the discussion in 4 modules. The first module covered in 3 weeks, the second module in another 3 weeks, and then third and fourth 3 weeks respectively. The first module have the title of AC excitation to RLC circuits. And in the 3 weeks, we will cover different topics within this module. The first topic, or the first title within this module, is the capacitor and inductor circuits. We will learn what are the capacitor and inductor circuits, their nature, their units, their formula and equations to calculate them, how they behave in a circuit, especially AC circuits. So this module, week 1, we will discuss 2 points: the capacitor circuits and the inductor circuits. We will go through the circuit operation waveforms and formula, but for capacitor, we will see how to calculate current voltage, and how to compute the capacitances if they are connected in parallel or series, and to compute also the power and energy storage. While in inductor, also current voltage and the storage energy and the power, but we will also add mutually coupled inductance. Okay, at the end of this module, week 1, we supposed to have application of concept learned for analyzing capacitor and inductor circuits, and we will have practice some questions to be solved. I will solve a few of them, and you will solve the exercises. Now, first of all, you remember resistance have been discussed in level 1, and resistance actually is a passive element. Capacitor and inductance, which was to be covered in this week, is also both of them are passive element, but they store energy. Okay, you need to remember this. They are storing energy. For capacitor, it's to store electrical energy, but for inductance, which will be discussed later, it will store magnetic energy. So simply, capacitor is two plates. Between them there is insulator, and they store electrical energy. Okay, they don't produce energy, but they store energy. And example, one of the application is that we use them in microphone, as we are going to see later in the discussion, and they are represented in different ways. You see here as a cylinder, different size, as you can see here, and different shape. Some of them porcelain, some of them let me say they use different insulator port pin. I will talk about it later inshallah in this module, and their size is different. Their size also is different. Now if we define the capacitor and its energy storage, we store energy between two blades. As you can see here, this is blade number 1 and down blade number 2, and this is here is the insulator, okay, which is called dielectric, as you can see here. The dielectric is insulator. It's not conducting the electrical current, but the plates here, as you can see here, the plates, the upper one and the lower one, are conducting the electrical current. The dielectric could be any insulator. It could be air, just air. It could be mylar, it could be polyester, it could be polypropylene, ceramic, mica, and so on. Different materials, okay? The main formula representing the capacitance of the capacitor, which is represented by C, equal to Q over V. Q is the charge, electron charge, or the charge, let me say, and V is the voltage across the two plates. Or simply, we can rewrite this equation Q equal CV. You know CV, okay? It's easy to remember. Q equals CV, okay? Q in coulomb, C in farad, V in volt. Okay. Now, just a minute. Next slide. Okay. You see here, C equal Q over V, or V could be written Q over C, or Q equal CV. All of them coming from the same formula. Here you see the current in this figure. The current follow through the wire to the plates. Here the positive charge stored, and here the negative charge and the insulator or dielectric between them. It could be simulated, the idea, by looking to the fluid flow analog for capacitor. And you can see here it's like water coming here, the current of the water coming here, and there is here elastic membrane, so the energy go through this elastic and go to the other side. It's represented by this simple two plates, plate 1 and the other one is a curved one. Current will follow here and voltage across the capacitor. By the way, it's important to know that DC current flow through a capacitor. No, it doesn't flow through, only AC. Okay, when we apply DC through the capacitor, directly it will be fully charged and no current will follow. But AC, because it's a fluctuate between positive and negative, then it's store and release energy every part of the cycle. Now let's see how we deal with the capacitors, how we calculate current, voltage, power, energy, and so on. Now determine the current for a capacitor. The voltage is given. You see the circuit? This is a capacitor, which is 1 microfarad, and this is the voltage apply across it, and current will follow here. He asked me to plot the storage charge and the current through the capacitor. We will see how to find the charge and the current. Now don't forget Q equals CV, right? CV. Now if I have the voltage here given as a figure, okay, we need to find the voltage as equation. How we find voltage as equation? You see here, from 0 here to 2 here, we have this straight line. Okay, from 2 to 4 we have constant value, again straight line but constant one, and from 4 to 5 we have another line. Let's do it on this and you will understand it. Have a look here. If I want to come to write the voltage V of t, function of t, equal, open parentheses and say from 0 t, this is the time, okay, lower than 2 microsecond, and from 2, this is t, as you can see here, okay, lower than 4, and from 4 t, between 4 and 5, still microsecond, okay. So you can see here, this is a piecewise function. It means contain 3 pieces, 3 parts. Part when t between 0 and 2, and part between 2 and 4, and part between 4 and 5. Okay, microsecond. Now you see from 2 to 4 it's clear, it's 10 directly, it's only 10. Any time fair between 2 and 4 microseconds, the voltage will be 10. For this one, we can find it by having 2 points. We can use the formula to find the straight line equation. You can see here, this point is 0, 0, right? While this point is 2, 10. You see here, we can write this point is 2, 10. And the origin 0, 0. So if I want to find equation, you remember y equal, this is from foundation, right? M, okay, C, x plus c, where m is the slope. As you remember, it is y2 minus y1 over x2 minus x1. You already studied this in secondary school, in foundation also, okay? Or we can write it directly, y2 minus y minus, okay, sorry, y minus y1 equal m x minus x1, as you can see here. Okay, now you can see here, if we substitute this point, I mean here, this one will go to 10, and this one will go to 2, and m is this one. We substitute, we have 10 minus 0 for y, and 2 minus 0, which give me what? 5, because 10 over 2, 5. So we have m, we have the point, we find the equation. This equation is found and written here, okay? As you can see, I will write it here. I repeat the same procedure for this point, this line. You see this line? Also, I have here point, I have here point. I need 2 points for straight line equation. Then I substituted. I got the formula for the other part. In this way, we convert this figure into a formula or equation. Now, if I want to find charge, then I will say CV. So I just need to multiply. Just multiply the value. 1 micro is 10 to the power minus 6 C by V. If I want to find the current, okay, coming from charge, okay, we can write the current formula is I equals C dV over dt, rate of change of voltage with respect to time. So C also is given to me, which is 10 to the power minus 6, which is 1 micron, as you see here, also here in the circuit. Okay, dV over, just we need to substitute. We substitute the first part, the second part, and the third part. You see here, V equal Q over C. Okay, this is another example. A charge of capacitor is given by Q equal 10 to the power 6 sine 10 to the power 5t. Here he gave me the charge. Find the expression for voltage. Okay, I know that Q equals CV. So V equal Q over C. Just need to divide, as you can see here. Divide the equation here by the capacitor, which is 2 micron, 2 by 10 to the power minus 6, as you can see here, and simplify. What about the current? Current equals C dV over dt. We have V. Can we differentiate? Sine, differentiation of sine is cosine. You see? So just differentiate it, it will be directly appear. Now if you ask me to determine my voltage for a capacitor given the current. Now current is given, find the voltage. We know that if current given, I can find the charge by integrating current with respect to time, as you can see here. And voltage by 1 over C integrating also current. So here, rather than we differentiate, we integrate. Again, don't forget, you have I for the capacitor equal C, don't forget this formula, dV over dt, right? So if the voltage given to me, as you can see here, the voltage given to me, I differentiate and multiply by, see what I got, current. What if the current given to me? Just back to this equation, cross multiply and rearrange, you have this formula. which is rather than differentiation, we will integrate. And then rather than we multiply by C, we divide by C, as you can see here, right? Now this example, if you can see, he gave me this sinusoidal waveform. The maximum is 0.5, the minimum is minus 0.5, here time in second, and one fill period is 2 pi 10 to power minus 4. So the charge, if I want, is integrate the current. So just substitute the formula, as you can see here. Integrating of sine is minus cosine, right? And we substitute from 0 to t. We have formula for the charge. We can plot it. You see here, it's plotted. What about the voltage? You remember we say Q equals CV. We have Q and C. Let's find V. Just divide Q by C. We have already Q. We integrated in the previous slide. We got it. What about power and energy? If we have voltage and current, can we multiply them to find the power? Yes, we can. Now, also, if I have the power, can I integrate it with respect to time? Yes. What it give? It gives energy, as you can see here. These are principles. You already studied this in ELEC2200 in level 1, right? These are principles. And by the way, we can find formula for the energy. Formula for the energy directly. As you can see here, P dt is the integration of P dt. And since P is VI, as you can see here, and since I is C dV over dt, as you can see here, we can write it here in this place. Now cancel dt with dt, what is left? V dV. Integrating V dV would give me V square. So very simple. The energy of the capacitor is 1 over 2 CV square. We can definitely substitute because we know Q equals CV. We can substitute to find the energy in terms of Q and V, in terms of Q and C, as you can see here. It's very easy. But this is the main. This is the main. If you have the capacitor, then just 1 over 2 CV square will give me the energy. Now, current, power, and energy for a capacitor. Now, as you remember, this is the voltage given here from 0 to 1, from 1 to 3, 3 to 5. You can see here, I wrote the piecewise function for the voltage. First of all, you need to find the formula from the figure. You see here, from 0 to 1, these are the first part. From 1 to 3, this is the second part. And from 3 to 5, this is the third part. For this part here, from 1 to 3, it is constant, 1000. I wrote it, you see here, 1000. But for the first part, I will find it using the formula of straight line equation, because you have 2 points. This is the origin 0, 0, and this is the point which is 1 for x, 1000 for y. So I found the equation, just substitute, found the slope, substitute in the straight line equation, and then find the formula. It's worth mentioning here, you can see here that the equation here for the voltage have positive sign. Why positive sign? For T? Because it's growth, you see here, up. While here this part from 3 to 5 is going down, decay, so T have a negative sign. You will find this in the equation. When you substitute in the equation, you will find it. Now, since we have the formula for the voltage, I want to find the current, which is C dV over dt. The same limits, the same range, let me say range for Y, or for the current, it is from 0 to 1, 1 to 3, 3 to 5. Now I differentiate this 1000 T and multiply by the capacitor, as you can see in the formula. It gives me this. I differentiate 1000, which is constant, give me 0. You see here, 0. I differentiate this and also multiply by the capacitor, it gives me this equation. You see, it's straightforward. Now I have the current, I have the voltage, again, the same range, just multiply voltage by current. It means multiply this part, sorry, this part for current by this part for voltage. It gives me this part for power, and so on for other elements. You see, I plot it here. When you got it, you can plot it very easy. As example, this is 0 from 1 to 3. This is 0. 10t, you can write it the maximum 10, and this is 10t. And 2.5 by, you can write it, plot it also, it will be decay. Okay. Now energy is the last part, which is omega equal 1 over 2 CV square. We have the voltage, just square it, multiply by C, divide by 2, you got the energy in joule. What, second or joule? Now let's take example. Charge, voltage, power, and storage energy. The current through 0.1 microfarad capacitor is shown in figure. You can see here, this is the current. It's a square wave. So we have range from 0 to 2 and from 2 to 4. That's it, because from 4 to 6 it's repeated itself again and again and again. It's a repetitive function, right? He asked me to find the charge, voltage, power, and storage energy. Okay. Now we will come to say from 0 to 2, we will find the charge. Okay, integration of current with respect to time. How much the current? 1 milliampere. So 110 to power 3 dt. Integration from 0 to t. Okay, from 0 to t for the first part, from 0 to 2 here, as you can see here. Now we integrate, it will be 110 to power minus 3t. Now the second part is from 2 to 4. Okay, from 2 to 4, the value here, as you can see here, minus 1, 10 milli, so 10 to minus 3. Okay, this is minus 1, 10 to minus 3. Okay, started from where? From 2. Ending where? At t. T could be any value between 2 and 4. That's it? No, we need to consider the previous state. What do you mean by previous state? When we started from 2, how much the current was at that time? Very simple. You see here, we integrated from 0 to 2.